Hey, hello. Hi,
Hey,
Jen.
Darling, how are you?
Good yourself?
I'm very well. I'm very well. Thank you. It's great to see you.
Yeah, great to see you.
Are you at home?
No, I'm at office actually.
Hi, me too. Yeah.
Things. So where are you based? You in Melbourne?
We are affiliated with Uni Melbourne, but we are also kind of standalone entity.
Okay.
Um, we are based in the building of Pioneer Hospital.
Okay.
Yeah.
Sure.
So yeah. We have done a lot of, we're doing a lot of collaboration with Dr. Zhong Yang.
Yeah.
So that's our common link. Yeah.
Yeah. It's good.
It's great to hear um, some work from you today.
Yeah. Yeah. Looking forward. Well, look, thanks for the invitation.
No
I'm looking
problem.
forward to the presentation. Yeah.
Yeah, I have known nothing about MRI and PET scan and looking forward to learn
Sure.
more about it. But hopefully the application will inspire people who are who can use this. Yeah.
Yeah, hopefully. Yeah. Let's
It can be
see.
used in many areas.
Yeah. Yeah. Well, that's a hope, right? Oh, yeah, I did put a little bit background into my presentation, so hopefully that will bridge to a certain level the gap from the
Yeah,
audience.
yeah,
So hopefully that will be useful.
yep, absolutely, no doubt.
Hmm.
Yeah. Um, just give it a 1 2 minutes
Oh,
while the page people are coming in. Yeah.
yeah.
Um, let's give it 1 more minute. Okay, it's 1 past 5. Should we make a start?
Um, yeah.
Yeah. So welcome everyone. Yeah, thank you for joining us in this webinar series of AI and its application in healthcare. My name is Jang He. I'm the research project manager in Center for Eye Research Australia. We are based in the beautiful city of Melbourne, Australia. Um, the goal of this webinar series is mainly to help to connect and build the connection, collaboration between clinicians and researchers and AI scientists. And we thank the Medical Research Future Fund, which provides the funding for this webinar series. This is actually the fourth series. Previously, we have excellent speaker and great topics, so it goes beyond eye research, even though I myself is in the area of eye research. So this webinar series will cover any area in AI and healthcare. And today we have our invited speaker, Dr. Zhaolin Chen, who is the world-class expert on the application of AI in medical imaging. Zhaolin received his PhD in Monash University, and his work mainly focused on imaging, medical imaging, and developing new methods in MRI and MRI PET scans, including data acquisition, image reconstruction, and image analysis. And also, of course, machine learning in medical imaging. So it is with great pleasure today we get to hear the latest development of Dr. Zhaolin's work. Just before I hand over to Zhaolin, just a housekeeping. While you guys are hearing the talk, if you have any questions, please feel free to type it into a Q&A or the chat box, and I would pass on to that questions after the presentation. All right, thank you. So yeah, passing on to you, Zhaolin.
Great. Thanks, Jen, for the nice introduction. And also thank you for your invitation to present in today's seminar. And also thank you thanks Zhongyuan for inviting me to this this talk as well. Perhaps let me just share my screen. It says host disabled participant screen share.
Oh, let me see how to. Okay, let's try again.
Yeah, it's working. Great, thank you. Okay, let me full screen. Can you see it?
Yes.
Okay, great, excellent. So, in today's talk, Today's talk, I'm going to talk about artificial intelligence for MRI and PET image reconstruction and their clinical applications. So here's an overview of today's presentation. I will touch briefly the scope of our research in MRI and the PET reconstruction using deep learning. I'll talk a little bit on the recent development in the literature in this area. Before I'm moving into our approach using biophysics-informed deep learning methods for MRI and PET imaging and their applications. In particular, I will talk about three technologies we have been developing. The first one being MoCoNet, ReconNet, and SUNet. Okay, I will touch upon the details during the presentation for those three topics. So the scope, really, if you look at the overview of imaging, medical imaging workflow, whether it's research or clinical research, the first step is the scheduling and patient preparation. Okay, and once the patient's ready, we go into data acquisition and image reconstruction from the machine. And after that, we have interpretation, and the reporting from the images. So if you think about AI, so AI has been used in all these areas, and many recent developments in particularly for data interpretation and reporting, and the many products is available in the market now in this area, and the many research orientations in this direction. My research is particularly focused on a step before that. It's called image acquisition reconstruction. So that's the instrumentation related aspect. Okay, so that's the area I'm focusing on today. And the topics, as I mentioned before, there are three topics I'm going to touch upon. The first one is reduce motion artifacts during medical imaging. So our technique is called MoCoNet. And the second topic I touch a little bit is accelerated magnetic resonance imaging to make imaging a bit faster, more efficient. And the last topic I'm going to talk about is low dose PET imaging. Okay. So now, if you look at my research area, the workflow I'm focusing on, the module I'm focusing on, data acquisition and image reconstruction. So a subject come into the scanner. The scanner will push out measurements, which is what we call raw data sets. In MRI, it could be case-based data. In PET, it will be least small data sets, but they all just raw data sets before images. And then these raw data sets will be passed through an image reconstructor and then generate an image, and which we hope that represents the subject coming to the scan, right? So that's really the workflow from instrumentation point of view. If we look a little bit more detailed from signals and the systems perspective, looking at that workflow again. So I have my subject, let's call the PF, which is the ground truth, which I don't know before. And then I have my imaging system, which could be an MRI, could be a PET. I will call it the G, an imaging system, which is we call forward model in the field. It is basically a function of hardware It could be MRI coils, PET detectors, and the geometry of those hardwares, plus a software which drives the scanner in terms of MRI's pulse sequences. But all in all, that's modeled by this G forward model. And then we have our measurement data. Again, that's called M, that's raw data sets. And what is the image reconstruction? And image reconstruction is defined inverse model, H, that maps the measurements to a subject space, okay? So that's the image reconstruction. So after this mapping, I have my image, which is an estimated subject, that's called P, which is different from PF. So when we're talking about image reconstruction, what we want to do, we would like a P, which is reconstructed image, to accurately represent the ground truth PF. However, we know in terms of human body or human, there's a variety of information in there. It's really depending on the contrast you want to image, the modality you want to use. PF can be very different. It could be magnitude images. For example, in terms of MRI, it could be T1 weighted, T2 weighted, or proton density weighted images. It could also be phase images and susceptibility weighted images for MRI. It could be a functional weighted images. For example, in particular, blood oxygen level dependent for functional MRI. It could be diffusion weighted. So look at molecular exchange inside of a living organ. It could be a reduced tracer activity in terms of PET. So there's a variety of PF we can imagine. And in terms of accuracy, how do we want to represent PF? Normally we want minimal noise, right? We don't want to have a huge amount of noise in the image. We want to have a minimum artifacts. So for example, the motion artifacts is the one we want to get rid of. We want to have a minimal bias. So the images need to be homogeneous across the field of view. Okay, we want to have a quantitative accuracy, which is very important for PET imaging because the clinician need to draw an ROI inside the image and then measure the uptake value and determine whether this is normal or not normal. Okay, so those are the accuracy metrics. Well, you may argue, why do you need a deep learning, artificial intelligence in the whole workflow? Should you just invert the forward model, get a invert system using any deterministic approach? Well, you could. However, the problems come from these factors, the uncertainty or imperfection of the forward model during imaging, which are very difficult to model. Okay, that can be a factor. There's the imaging hardware that's not perfect. For example, there's magnetic field inhomogeneity built into the system. Okay, it could be limited to the fundamental physics principles. Okay, it could be man-made selections. For example, we often undersample the measured data to reduce scan time. MRI being very slow and costly. So we want to speed up the data acquisition. And the subject, the participant, moves inside the scanner, which often causing problems during examination. So those factors will cause the measurements, M, to be somewhat different from PF. Often it means lose information. Okay, so it's not one-to-one mapping. It's many-to-one mapping or one-to-many mapping. So depending on how you look at it. And that makes solving H becomes a opposed problem. And deep learning is very powerful in terms of solving very complex mapping issues and resolving image artifacts, for example, is proven in computer vision or image processing field. And nothing special with MRI. Those techniques can be very helpful in terms of solving the image reconstruction and data acquisition issue here. If you look at the timeline of MRI image reconstruction development, the first very early on MRI would be pointwise voxel-wise image acquisition and image direction as basically a Fourier transform of the measurements back to the image. It's very slow. The efficiency is very low. And during 1990s, it's moving into parallel imaging where you have multiple coils. So you can speed up the data acquisition by using multiple coils. So that's magnitude better in terms of efficiency. And then during 2000, the regularization. So we know while we're speeding up, increasing the speed of imaging, the image reconstruction quality is getting worse. So we may want to use some prior information to regularize the image reconstruction process. That's becoming really popular in 2000s. And starting from 2010 and onwards, computer sensing and low rank imaging as a very popular technique. So that's really take advantage of the sparsity nature of medical images. The issue being the small structures, very subtle changes inside the human body may not recover during computer sensing process or low rank reconstruction. However, that's still a very dramatic improvements over regularization previously. And then really starting from 2015, also deep models becoming visible inside the MRI, image reconstruction, and data acquisition. So then the deep models really just mapping a convolutional neural net between the measurements and the image you want to reconstruct using a supervised model or unsupervised if you want to use deep image prior and those type of technique, and parameterized by a theta. Yeah. Okay, in particular in this talk, I will focus on deep models a bit more. If you look at early works, for example, Zhu et al. Published this work in 2018, where they map directly from the sensor space, which is a measurement space I was referring before, to the image space using an end-to-end approach. So the technique they developed is called AutoMap. It maps from the measurements to images, including any deterministic transformation, a domain transformation. For example, in this particular case, in MRI case, it would be Fourier transform in between. So they use a fully connected layer to model Fourier transform. So that efficiency is very low. You can imagine for a MRI resolution normally is 1 millimeter isotropic. The image size in plane can be 512 by 512. So we certainly have a memory issue with this type of approach. However, the image quality demonstrated in their paper is quite dramatic improvements compared to conventional approach. So they tested the different sampling trajectories inside the MRI and different undersampling patterns. And in all scenarios, they have demonstrated the AutoMap is greater, is much superior compared to conventional image reconstruction in terms of the SNR and the image sharpness overall, especially if you look at this artifact here in conventional image reconstruction where deep learning in AutoMap, they can recover the image really well. Okay, so that was early type of approach in this field. Moving into 220, where there's a challenge. So it started from New York University and Facebook. So they initiated this challenge where they have a large collection of data and invited teams to participate in this challenge. And in this paper, they summarize what their finding is during the challenge. Okay, so they have 3 MRI contrasts. You can see from here, a T1 post enhancement and the T2 weighted and the flare, a T2 weighted flare as well. So where these are the 3 participating teams where they are ranked pretty high in the in their structural similarity index, for example, here. The whole experiment is 4 times acceleration, so which means the data acquisition downsampling. So data has been downsampling 4 times. If you look at the image quality, it's pretty close to the ground truth, except that this having these 2 images have a little bit of artifacts there, but overall they're pretty good. They virtually, if you compare these 2 rows, you can see a little bit smoothing artifacts, but the image quality is really well reconstructed. However, if you look at the closer, the issue comes if you have out of distribution data set. Okay, so in this particular case, the ground truth doesn't have this vessel, have this artery, where the reconstruction, even the top participating team, artificially introduced this, which is a major problem in medical imaging, right? So we can't have n=1 error. So this is not acceptable. So out of the distribution is a major issue in this field. It's still a major issue in this field. So these are the examples where you see the ground truth tells you something, but your reconstruction creates an artifact. The problem being the artifact is mimicking the anatomical structure. That's a major issue here. So, and also here you can see that it's almost like a vessel or a cortical structure in there. So the problem even becoming even more obvious in this work. It's from Anton in 2020, where they explicitly testing the out of the distribution error. So the whole experiment was they compared deep learning with conventional state-of-the-art reconstruction, where they try to introduce a small perturbation in the input. Okay, the input is the X, R's are small perturbation, very small. You can't see from the input. However, they test this small input whether they can create a large error in reconstruction. If you see state-of-the-art reconstruction, this is reasonably well controlled, assuming A is well defined. Okay, if A is not well defined, that's a different story. But overall, in good clinical setting, so that's not a major issue. But it's relatively less predictable in deep learning. A small perturbation in X you can't see during reconstruction may have a major impact. You see the image having this banding artifacts over there, which again causing problem. That's cause out for explanatory power of the deep models. It's a bit like a black box. We don't really know what is happening here. Again, that's out of distribution issue, the stability issue of the deep model overall. Without any perturbation, you can see the image reconstruction reasonably well. This is just an example of demonstrating the out of distribution issue. The field is still debating whether this problem exists with conventional reconstruction as well, or we just putting really a inferior experiments for deep models. However, this even is debating that there's certainly some of the issues are visible from these experiments. So now I want to talk about our approach where we think how to at least mitigate or improve the stability or the distribution performance for deep models. The approach we take is about physics-informed deep learning models for improving the out of distribution performance in deep models. So we know that medical imaging is a complex, for example, MRI is a complex interaction between tissue and the magnetic field. So it's a complex interaction between that, but it's still those interactions can still be modeled. If you use those information to define a regularization for deep models or as an augmentation to deep models, it can improve when the deep model reaches to the boundary, becoming unstable, how you observe the solution space. Okay, and then we define deep models according to the biophysics and use that for the three topics I'm going to touch upon today: the motion correction, the accelerated MRI imaging, and PET imaging as well. So I'm going to talk about the first topic here, the motion artifacts in MRI. So we know people will move inside MRI scanner. It could be because they are just elder people. They are kids. You can't make them stay still. They have an illness, and MRI is a long scan time. Imagine MRI has a resolution, typical resolution. You see the image on bottom, 1 millimeter isotropic. A small motion will create an artifact. Okay, it's hard to make sure people not moving even 1 millimeter in space, right? It's very difficult to keep still. And if patients moves inside the scanner, we have ringing artifacts, blurring artifacts, and ghosting artifacts. That's demonstrated here. So the first image, there's no motion, or minimum motion. There can't be truly no motion. There will be minimal motion here. We'll assume that motion is acceptable, is the highest image quality here. And if patient moves, you see that ghosting artifacts penetrating through the images. And if people moving a little bit harder, then you see a larger image artifacts. Okay, so like similar to when you take a photo using your camera, if you shake your hands, then the photo become blurred, and you can use deep learning model to stabilize your camera, right, in a similar way. So here's our setup of the deep models where it fits into the overall imaging workflow. So we have a scanner, patient inside the scanner, and we acquire the measurement space in this MRI's case space. And then we introduce a motion correction module here. It contains, as I mentioned before, a biophysics model here, which models the interaction between patients and the scanner. And then there's after the data acquired, there's a retrospective motion correction module here, which is parameterized by a deep model. And then we correct the motion and reconstruct the image. Okay, so that's the flow. This is the model we take. This is a deep learning model we take. If you're interested, have a look at the paper, but I'm not going to details of this. And so basically, we use a multi-resolution approach, or use ResNet, but with a multi-resolution approach, because if you think about the motion artifacts, it can be a local artifacts, but it can also be a global artifact. So the convolutional kernel better to see a different level of penetration. So you want to see that ringing artifact is penetrating a larger distance. So we use the inception ResNet encoder and the convolutional decoder in this case. So that's the fundamental reason we use this model here. So here's some simulation results. Again, we can model, as I mentioned before, we can model the interaction between patients and the field. Then we can generate the motion curve as a product. We know exactly how the motion being simulated here. So you see the reference. There's, for example, you look at the zoom in. There's no motion, but as soon as the motion comes in, you see the artifacts comes through, and with deep model with MoConnect in this case, the artifacts are being removed from this example. Okay. So this is not simulation. This is a motion controlled study where we have a volunteer, a participant inside the scanner. We did 2 scans. The first one without motion. So we asked the participant to stay still inside the scanner, do not move. And second, the participants would move, but we don't instruct how the participant moves. Okay. And then we use the DL, the MoCoNet to correct the motion artifacts. Again, the training data sets has nothing to do with this. It's a truly unseen case. The model doesn't know this this data set inside during the training. Okay, we show the motion artifacts is largely removed from the motion corrupted data. And after that, so that's really just an in-house experiment, and then we move to radiology. So we work with Professor Ming Lao at Alfred Radiology to really have a setup over there to look at motion correction capability inside a radiology practice. So we set up a DICOM server between image reconstruction and the hospital PACS, and then pushing that data through to the high performance computing for both for the first of all for the inference, but also for the active learning. But I'm going to show you the results only from the inference. So the model being trained only through the simulation, so through the biophysics simulated data sets. So the hospital data are not used during the model training at all. So the hospital data is coming from multiple scanners. They have a different field strengths, which is quite different from, and they have a different protocol. So the image quality is very different from one to another. I show you some examples down the track. And then we ask the radiologists to score the images. So we have a 5 scale in this case. So 1 being excellent, there's no problem. 5 being the images are very poor and unusable, and images corrupted. And it's continuously ranging from 1, 2, 3, 4, and 5. So then we sample a group report from this exercise, from this experiment. So with MoCoNet, we can see a consistent improvements. The yellow one is with MoCoNet, the blue one is without, for different brain structures. Okay, there's 9 brain structures we've been looking at. So radiologists are asked to view and score those 9 brain structures separately. Again, I remind you that lower score means the better image quality. So you see a notable reduction for all brain structures after MoCoNet. And ventricle has the lowest improvements, where small structures like phonics in the brain has the greatest improvements gain from this image quality. So overall, close to 60% of the data sets have been improved. And away from those 59.7%, 39.5% were not affected by motion correction, so which means the score didn't change. However, we also noticed that 28.6% were already at top score, highest possible image quality. So if you remove those 28.6, so effectively 10.9% remain unchanged. So based on the radiologist's view, 13.6% repeated scans can be avoided. So there's an estimate for hospital for each scanner is cost $100K US per scanner per hospital annually. So there's a large amount of due to repeating scans. So it's quite a bit that can be avoided. And there's 0.8% of the scans are degraded. So this a joint histogram demonstrates how the scores. So this is with motion correction, this is without motion correction. The off diagonal, bottom off diagonal means improvement segment, and the top diagonal here means downgrading. So which means without motion is better. So you see the majority of the distribution is coming from the, again, coming from the bottom segment here, diagonal. Here, the majority of are changing from, so for example, previously ranking 3, now it's ranking 2, there's 7% that one score improvements over there. So that's how you read this graph here. Okay, so I'll just give you a couple of visual cases you can view. So this is the motion degraded. You see there's pathology, there's this injury probably for this patient here, which during training we only use healthy subjects or simulate according to that, right? So it's truly unseen, and the motion corrected nicely removes the motion and without degrading the injury, yeah. And also in this case, it's quite severe motion here. The motion correction will just clean up very well. There's some residual artifact as you can see from here. This line here, it's artificial. It could be, but we're not certain yet. Thinking about it because of this motion shift, and the MoCoNet didn't remove that, so that's a residual. That's a problem. So that's with MoCoNet. I'm going to switch gear a little bit and move a little bit faster. So the second topic I'm going to touch upon is accelerated imaging in MRI. So we know MRI is slow compared to CT. It's a lot slower. So normally you have a 30 to 60 minutes scan time. So what people do is to speed up data acquisition by downsampling its signal. Okay, if we downsampling by factor of 2, I become 2 times faster. So from 30 minutes become 15 minutes. That improves greatly the radiologist throughputs. Okay. However, accelerated imaging amplify noise and create ghosting artifacts. Okay, you can see from this example here, without acceleration, you see the nice profile of these 2 cortical structures. You see these 2 peaks. With accelerated imaging, you see, first of all, noisy, and then the resolution of those 2 peaks are becoming poor. You can use a different reconstruction, however, it's still very poorly. The structure is not as good as the reference one. Occasionally, you can also see ghosting artifacts. Okay, so this is coming from this structure here due to, so this is aliasing due to undersampling the signal. We know we have to follow Nyquist sampling rates from signal processing point of view. If we violate that, there will be aliasing artifacts. So this is basically that. We have the structure folding back here. That's called aliasing or ghosting artifacts. So this approach we took is quite a little bit complex to view, but the blue box here is conventional, let's say conventional parallel imaging reconstruction technique, and the green box here is a end-to-end deep learning mapping technique. And we want to, so we introduce this reconstruction technique, so that augments the model, the physics space model with deep learning model. So the solution space now becoming a vector, you can think about is a higher dimensional space. So the ReconNet is a search in that high dimensional space. If the conventional image reconstruction gives you an accurate representation of small structures, or search, hopefully the solution will go there. The gradients will lead us to that. If the deep learning has a really good denoising feature, then hopefully the gradients will lead to that direction. So, and then we compared the ReconNet with parallel imaging, which is a conventional non-DL based approach, and with the end-to-end with a non-uniform sampling, which is the standard practice. So we compared the ReconNet with this. If you look at the zoomed version, well, first of all, the overall reconstruction error is lower. So this row are reconstruction error, I have to say. And if you look at the zoomed region, you look at those two lesions, the strength of a conventional imaging approach has good localization. The small structure are still being preserved, even though the noise is the issue here. You can still see the structure. Deep learning has really good denoising, but as I mentioned before, depending on how you train the model, if the model didn't see that structure, you may not physically reconstructing that. So with the higher dimension that you can search, you can leverage the advantage from both the physics-based solution space plus a deep learning solution space, give you a best representation of this lesion here, as well as the nice recovery of signal noise ratio from the original image. And this is another example, the panel on the right-hand side, another example here. There's a lesion, quite aggressive tumor here. See the zoomed region. You can see from the deep learning trained model, again, if the model didn't see that, this the model is going to reconstruct a blurred, which I wouldn't say this is too bad, but still compared to conventional techniques, a lot sharper in the edges, in the detail, the structure, the tumor core and the aggressive tumor, yeah, where this is a little bit blurred through. If you use a ReconNet approach, this demonstrates a better representation, better reconstruction, image quality overall. And motivated by the paper I mentioned before, the test stability issue, we manually put some words inside the image and to see whether the reconstruction algorithms can recover those. It's a bit of fun exercise. So there's a reference we have this, can you see it? With deep learning model, depending on where you put the sentence, if it's on top of the contrast enhanced tumor here, it's becoming really blurred out. It's becoming one thing here. But if you use the conventional physics-based approach, then even they are in the same region, you can still see this letter and here reasonably well on Y here. Okay, I think that really brings the advantage of using a biophysics approach to deep models. So really the last one I want to touch upon is the low dose PET imaging, moving away from MRI to PET imaging. So the approach we take is to, as I mentioned before, we have this physics-based model, and still having here for PET imaging, it's called cenogram, so different from MRI, PET, it's in cenogram, but nevertheless, this is physics-based model. This is deep model, and on top of that, we try to quantify uncertainty as well. So I will show you a little bit on the uncertainty aspect of the importance of being able to estimate the confidence of your model. So this is a busy slide, but I will draw your attention to the input, and these are comparing different models in the literature, M1 to M5, And our SUNET model is shown in the last column here. So the model is trained, it's only in the top row. And then we feed a further degraded, so even lower dose PET images experiments into the reconstruction without retraining the model to see what's performance you can get from different techniques. So M1 is a deep image prior. So deep image prior is for image denoising. They can't really recover the image. So this is reasonable. The performance is not for this task. And M2 like a UNet ResNet based architecture and approach. I won't go into details of all the 5 models. The take-home message here is even the model is trained with this low dose to high dose mapping with the physics built in the sinogram model process you can introduce. So even extremely low dose input, you can still reasonably reconstruct the image without retraining the model. It's because of the physical process that gives you that guarantee, you know what is you're trying to recover. And I want to talk a little bit on the uncertainty estimation. So the uncertainty map, besides the reconstruction, if you do, for example, monocolor dropouts during the modeling, you can estimate the a uncertainty map from your model, which can be very useful. For example, in this particular case, this is an uncertainty map sigma. If we threshold this map, we can see this region. Yeah, that's where the majority of the error is coming from during this reconstruction. So there's the increased uptake in this region. So we just want to highlight that it is possible to estimate the uncertainty if you choose to during your deep modeling. So then I will just quickly show you the application of SUNET in our functional PET functional imaging, where we do visual stimulation experiments using PET imaging. So the experiments is we have participants close the eye for a certain period and show a checkboard stimulation to visual cortex, and then another resting period. So then the metabolism in the brain, we should have increased uptake of the energy uptake, the glucose utilization inside the brain. So that's what we see in this curve. Yeah. So with our SUNET, we can recover this curve and recover the brain activation area in this reasonably well. Okay, so that's a visual cortex. And if you compare with the conventional, just do a Gaussian smoothing with a low dose PET, the recovered signal is very poor, and the localization of visual cortex is relatively poor as well. And the image on the left-hand side, I should tell earlier, but image on the left-hand side demonstrates the visual, give you a visual impression of the image quality using a SUNET type of approach. So clinical PET imaging having 20 to 40 minutes binning window. These data are 30 seconds. So it's not just one order of magnitude shorter, it's extremely short. It's 30 seconds PET, you get in this type of image quality. And if you use deep learning, you can recover to reasonable. I think that's a really great potential for deep learning moving into this for helping in this area. So okay, I'll stop here. So basically, in this presentation, I showed you 3 developmental areas. We're still further developing in this area. we try to use a biophysics approach for deep learning, which underpin a couple of application development in our research. So we have a MoCoNet I showed you for motion correction, ReconNet for accelerated imaging, and SUNet for PET imaging. So before end, I will just want to acknowledge my collaborators, my team, and the international collaborators and the funding agencies. So especially Dr. Kamlesh Powell and Dr. Viswana Sudarshan, they are major leaders for developing all these solutions. I have to acknowledge them for their contribution. Thank you. I would like to conclude, and if you have any questions, I'm happy to answer. Thank you.
Thank you, Zhaolin. This is actually fascinating work, showing that how fast your technology is developing, and yeah. So for people in the audience, if you have any questions, please feel free to type it in the Q&A or the chat box, and I'll relay on to Zhaolin. I have a question. I just think about the impact of this for clinicians, and it's enormous if you can cut down scanning time by undersample, for example. And I just wonder whether you can comment a little bit more on the impact where this can be used in, for example, a clinical emergency. I understand that, for example, in the event of a stroke, right? People make basically the go-to imaging is CT rather than MRI. And one of the reasons the MRI takes a lot of time. And I wonder how much time you can push to save before you get the technology, before the technology reaches limit, you start to have a limit in correction.
Yeah, that's a really good comment, John. I think you touch about you are really in the right direction. MRI being very slow, so currently in practice, so the acceleration factor we can use 2 to 3. That's pretty much we do. With deep learning, there's possibility to double that or triple that even. However, the auto distribution issue becoming a major problem. So this is just one direction accelerating that, but you can also using better hardware, make the scan a bit faster. There, of course, a fundamental limitation of how MRI responds, because the T1 relaxation, the fundamental physics limits the signal. So that's something we can't change. But with all of that, the first MRI scans being 4 hours, to now we have one contrast. So a 3D brain that takes 5 minutes, for example. There is a general consensus from the field, from people. We want eventually make MRI become a CT scan time, just a step and shoot and leave. Takes time to arrive that point. So 1 minute, there's possibility, do a 1 minute really short scan. So that could be applied to a lot of issues with auto distribution I just mentioned before. We have to make sure it's really robust. N=1 testing is just not enough, and it's just more clinical validation. But deep learning really, I see the potential to move the speed, to significantly reduce the current imaging speed, let's say.
Yes, dramatic impact this research can bring in terms of reducing the exposure to radiation and giving a higher resolution of the lesion. So yeah, great work. Hopefully we'll get there one day. Definitely heading to the right direction. We have another question from Shazad, if I pronounce that name correctly. It was mentioned that thanks for the great talk. Can your SUNet be used as part of the method for reducing the acquisition time for the PET scan?
Yeah, I think the goal is to reduce the acquisition time, or reducing tracer, so low dose, but also reduce the time. They are sort of a similar problem, a dual problem, but reducing time, depending on how the tracer being injected, there is about kinetic process. So the tracer need to arrive the tissue and then you can reduce. So certainly can, but the amount of reduction may be different from the dose reduction, as I mentioned before.
Yeah. Thank you. I have another question related to research. I wonder whether you have experience of bringing this kind of tool to other imaging, like in the retina, we use what we call OCT, which is very similar to ultrasound, except it's not using sound wave, but use light wave to do the imaging. We get a cross section of the retina, and potentially by reconstruction, we can get a 3D of the retina. One of the problem in research, also in clinic, is patients are moving, breathing, right? And then it causes artifacts. Do you see this potential to expand this to other area of medicine as well?
Yeah, I think that's a great comment, John. I think the philosophy, the concept, it has been developed. The first time I see people using modeling the thermodynamics of the atmosphere, using really building the complex physics model, and then with deep learning to underpin some of the data analysis on top of that. So I think using physics, building in physics into the deep model, and then you cascade between the two, can provide quite a bit advantage in terms of motion, at least in our experience in MRI. So I can imagine if, of course, I don't really know the problem, but if you can build in the physics, how the eye movements you can track, then you can correct in that perspective. So inside of MRI, there is for some experiments we do eye tracking. So perhaps it's possible. I'm not really 100% sure, but if that can be tracked using a response signal somehow, and then that can be built into the deep models where you know this is moved, maybe.
Yeah, but can something be done post hoc after the images been formed to correct those artifacts?
I think so. So our approach, most of them I showed you are retrospective, apart from the prospective motion deployment. But the model is in there, right? We don't need so a lot of simulation are done before the X-ray experiment. So, but then you do need to simulate a lot of the scenarios, all different interactions between patients and the scanner, and then create that database, a simulation database, and then use that to train your model. And then retrospectively, if the actual experiments falls into that distribution, that should be fine. But the limitation is you really have to simulate all sorts of experiments. I can imagine with the eye movements is really complex. You know, the different combinations can be quite a lot. The same with MRI, even it's slow. You know, the different combination for artifacts. You know, some of the artifacts show you really nice Gibbs ring type of artifact ribbons. Some of them are just duplicates. You know, the combination, the combination can also be quite extensive. We need to think about all those scenarios. I think in that similar setting, it could be possible, but I can't comment too much of details in that.
Yeah, that's great. Yeah, I actually have more questions about image analysis and stuff, but I think it's because it's probably slightly outside your area of this talk. But also because we are also reaching the end of the 1 hour. So yeah, maybe we can just wrap up here. Oh, actually, we'll have another comment from Beta. Beta says, thank you so much. This workshop gives us a big picture how the imaging tools improve dramatically and how it will be used in the future. So it's a nice comment, several question. Yeah.
Thanks.
Yeah, thank you, Zhaolin. It's really, truly fantastic. It's truly a pleasure to hear your most recent work. Yeah. So yeah, thank you for joining us, everyone. Yeah, all the best for your future work. Bye.